To resolve the local Geometric Langlands program for ramified cases, we have to look at how a data stream behaves at a prime number. In the arithmetic domain, we see turbulence, a sudden jump in conductor exponents. In the geometric domain, that same point manifests as an irregular singularity on a Hitchin-base space. This table provides the translation dictionary. It shows that the local root numbers used by number theorists are the same structural data as the Stokes multipliers used by geometers. Logos field theory treats these arithmetic packets and geometric shapes as two observer coordinates tracking the same underlying Adelic data stream. The process begins when the stream hits wild ramification, an arithmetic obstruction where the local Galois parameter can no longer ignore the inertia group. We measure the depth of this chaos using the Grothendieck-Swan conductor, A of P sub V. The formula extracts the data by separating the discrete topological filtering from the wild p-adic exponential filtering overhead. Solving this equation yields a single integer, k sub v. This integer is our baseline data payload for the rest of the translation. In the geometric domain, the integer k sub v dictates the exact degree of the polynomial singularity in the field's kinetic operator. The local field equation for the Higgs field develops a pole of order k sub v, as shown in this denominator. At this puncture, a standard metric would infinitely diverge, causing the variational principle to fail. J-theory handles this by injecting a singular Poincaré-Arakelov regularization term into the metric template to keep the system well-behaved. This modification contains the arithmetic chaos inside a stable geometric boundary, allowing the field to transmigrate across the puncture. Because the space is now warped by this pole, the standard loop algebra governing the gauge group must deform into an irregular affine Koch-Moody algebra. This new commutation relation is designed to survive the presence of the pole. It starts with the standard Lie translation structure and the central extension based on the level. But look at the third term. Based on that Kronecker delta, what happens to the Laurent modes as the data stream transits around the puncture? The modes are scattered. The irregular Higgs residues act as a background arithmetic force field that breaks the global conservation of mode numbers. This scattering means the energy-momentum tensor must now explicitly incorporate the irregular residues. The underlying conformal geometry can no longer remain static. It must evolve alongside the data stream's fluctuations. We calculate this evolution using a modified Sugawara construction, which yields an effective central charge for the representation. At the critical level, the system produces a massive commutative algebra of observables, which dictates the stable classical geodesics of the metric. However, when the data stream shifts to a non-critical level, these classical geodesics dissolve. This critical deficit manifests as an effective Planck constant, hf, which quantizes the moduli space. The solution space spreads from a single path into a spectrum of conformal blocks, turning the metric template into a fluctuating quantum fluid. To ensure this quantum fluid remains consistent across the entire Adel ring, the framework enforces a global level inversion rule. This is the Langlands level duality equation. Because the shifted levels of these two dual algebras must multiply to exactly 1, the system behaves as an arithmetic S-duality. This equation maps a strongly coupled, highly fluctuating state on one side to a weakly coupled classical stabilization on the dual side. This inversion ensures that the chaotic quantum behavior triggered by a prime number is always balanced by predictable classical geometry on the dual side. The pipeline is complete. We measured arithmetic chaos as a Swan conductor and carved it into a geometric singularity. We built the irregular algebra to survive that singularity and then utilized level inversion to find a dual stable state. This four-step sequence provides the mechanical resolution to the local Geometric Langlands program for ramified cases.